Japan did not simply build over water. It challenged the ocean itself. Between Honshu and Shikoku, the sea once decided how people moved. For decades, ferries carried life across these straits, but every crossing depended on conditions. Fog, storms, and currents could turn routine travel into a dangerous calculation.
Japan began asking whether islands could be connected permanently through engineering instead of luck.
The answer became a network, not one bridge, but 3 ocean crossing routes. One crossing stood apart, the Akashi Strait, deep, busy, and unforgiving. Any bridge here had to leave Japan's maritime traffic moving safely beneath it.
The first challenge was not above the sea. It was hidden below it.
Engineers had to read the seabed before they could trust it.
Beneath the waves were layers shaped long before Japan planned a bridge.
The tower locations had to be chosen with almost unforgiving precision.
To build underwater, Japan first built enormous steel shells on land.
Even moving the foundation pieces required marine engineering on a massive scale.
The caissons had to descend through current, weight, and uncertainty.
Before concrete could carry the bridge, the ocean floor had to be prepared.
Inside the steel shell, concrete turned a temporary form into permanent resistance.
The foundations were not delicate supports. They were anchors against the sea. From those hidden foundations, the bridge began climbing into the sky. The towers rose high enough to let a maritime highway pass below. In a suspension bridge, geometry is not decoration. It is survival.
The cables would pull with extraordinary force, and the land had to answer.
Before the main cables existed, thin lines crossed the impossible gap first. Temporary catwalks turned open air into a narrow construction floor.
The main cables were not lifted whole. They were spun wire by wire.
Thousands of steel wires became one continuous promise of strength.
That sweeping curve is gravity translated into engineering.
From the main cables, vertical hangers would carry the road below.
The road across the strait arrived in sections, suspended piece by piece. Each lift demanded calm timing in a place rarely willing to stay calm.
Slowly, the empty span began turning into a road.
Then, before the bridge was finished, the earth moved. The unfinished structure had faced a real test years before opening day. The towers shifted, and the final span quietly became 1 meter longer. The bridge did not fail. It forced engineers to adapt.
A great bridge survives not by being rigid, but by moving correctly.
Earthquakes were only one threat. The sky could attack the bridge too.
The roadway had to cut through wind without becoming a sail.
Tiny vibrations can become dangerous when a structure is this large. Hidden inside the bridge are systems designed to calm its motion.
Even sunlight changes the bridge, expanding steel across the day.
Expansion joints give the bridge space to breathe without breaking.
What once seemed impossible became a road people use every day.
Kobe and Awaji were no longer separated by schedule, weather, and waiting.
The Akashi crossing was only one piece of a far larger network.
Farther west, another route stitched islands and channels into a continuous crossing. At Naruto, tidal currents revealed how alive these waters really are. Together, the routes changed the inland sea from barrier into corridor.
But the Pearl Bridge remains the most dramatic symbol of the challenge.
At night, the engineering becomes almost invisible beneath the beauty.
Opening day was not the end. It was the beginning of maintenance.
Salt air is patient, and steel must be defended every day.
We're going some inspiration.
The main cables carry the bridge, so protecting them protects everything.
Inside the bridge, hidden corridors turn infrastructure into a living machine. Sensors help engineers hear changes the human eye would miss.
The bridge is watched because the weather never stops testing it.
A bridge this large is also an operating system for traffic.
Safety is built not only into steel, but into space.
Below the road, ships continue moving through the same ancient channel.
Only at human scale does the bridge reveal how enormous it really is.
At the tower tops, steel force bends without breaking.
The roadway hangs from cables, but the entire landscape helps carry it.
At each end, concrete resists the pull of the suspended world.
A bridge matters only when it connects smoothly to everything beyond it. For freight, reliability can be as valuable as speed.
The crossing became more than infrastructure. It became a landmark.
But permanence came at a cost, measured in billions and decades. The bridge's story includes engineering triumph and the burden of repayment.
Every mega project leaves one question behind. Was the transformation worth the price?
The bridge made movement less dependent on the moods of the sea.
The dream of connection was shaped by memory, caution, and loss.
The bridge did not conquer the sea. It learned to live above it.
In Japan, the ground itself is part of every engineering calculation.
Seismic design begins with accepting that the Earth will move again.
Controlled movement can protect a structure better than absolute resistance.
After storms or shaking, the bridge must be checked, not assumed safe. The bridge survives because people keep returning to inspect it. Paint here is not decoration. It is armor against salt. Keeping moisture away from steel can extend the life of the bridge.
Some of the most important work happens when the bridge seems asleep.
Beneath the road is a steel landscape most drivers never see. Even rain becomes an engineering problem when steel and salt are nearby.
When storms intensify, the bridge becomes a managed risk.
The sea can rage below, while the structure absorbs the test above. Resilience is not never being tested. It is returning after the test.
The lessons of Akashi continue into every extreme bridge imagined after it.
Records can be surpassed, but engineering firsts still change what seems possible. The achievement was never just length. It was survival in this place.
Much of the bridge's genius remains hidden below the waves.
Down in darkness, concrete continues doing the quiet work of resistance. Above the water, steel tension holds the impossible shape together. The strangest miracle is how quickly impossible engineering becomes ordinary.
From shore, the bridge looks permanent, almost inevitable. But nothing about this crossing was inevitable.
Every foundation, cable, joint, and sensor had to belong to one system.
Nature has not stopped testing the bridge. It never will.
Impossible projects begin by respecting what could destroy them. Across dark water, the bridge turns risk into connection.
The crossing endures because it was designed for a restless world.
Japan's deep-sea bridge proves the impossible must first survive reality.